In this upcoming tutorial, we will discuss the modeling of the robotic hand using robot kinematics and dynamics. In the previous tutorial, you learned that you could build a simulation to evaluate or even predict how your robotic system will perform in a real environment. The simulation allows you to test and see your design before spending time and resources to actually build the robotic design. However, how to represent this robotic system in the simulation environment is still unclear. And that's what we will discuss in this tutorial. Let's first have a recap of what we learned in the last tutorial. You were introduced to different simulation tools and platforms. You have learned how to define the environment, put your specific robot design into this environment, and then model the softness in the simulation. But some important elements are actually missing. How does the robot move? For example, how would the rotation or the angle of a joint affect the position of the fingertip? What does the angle mean to us from a robotic control perspective? That is, we are using motors to control the hand. And how does the motor's position then correspond to the robot joint angles and eventually to the finger's orientation? So what do you need to input to get your robot hand towards a certain position? How much force is needed for the robot hand to hold onto something so that it's stable? And what does it then actually mean to the motors? These are the elements that are missing for the simulation to work. And they can be solved by studying the robot's kinematics and dynamics. So here is the plan for this tutorial. We will walk you through what the robot kinematics and dynamics are, how to implement them, and then lastly, how some of these examples would look like on the 5-hand. Robot kinematics and robot dynamics are the study of modeling the physical behavior of robots. It's part of those mechanics that focus on the movement and the forces that act on the bodies of the robot. To be more specific, robot kinematics discuss only how things move. For example, how to get a fingertip to a certain location and orientation through the combination of the individual finger joint angles and the robot arm angles. So in this picture that I'm showing you here, it would be how to get X, Y, Z, alpha, beta, gamma, to go from theta 1 all the way to theta 6. While robot dynamics discuss the motion and forces during movements, and that is what the torques of the motors need to do in order to get the hands to hold the ball firmly that the hand is grasping. So some related questions towards robot dynamics would include things such as simulating them, then controlling them, designing, optimization, and actuation. So in this course, we use the Franker robotic arm as the arm for the robotic hand. The Franker arm is a conventional rigid linkage, and it has rotational joints in order to move. It consists of actually 7 rotational joints, and that makes up for 7 degrees of freedom. Normally, with 6 degrees of freedom, we could already uniquely describe the pose of an end effector that is the end of the robotic arm. But with 7 joints, we have 1 more degree of freedom, and that actually ensures the versatility in a 6 degree of freedom 3-dimensional world. So for the simplicity and ease to understand in this tutorial, we will only discuss for now things in 2D. But you should also be able to calculate the kinematics of a Franker arm after this tutorial. The only difficulty is that it is in 3D, so the equations would be much more complex. But the essential ideas should be the same, both in 2D and in 3D. So to discuss robot kinematics, we need to first know how to define a point or link in space. In a Cartesian 3D space, 3 values could represent a point with respect to a Cartesian reference. And the link would just be a vector between its 2 endpoints, just as the xp and the rap are shown here. Links could be added or subtracted to get new links. So now the reference frame must be the same when doing addition or subtraction. Here the lowercase in front of the r denotes which reference frame this is expressed in. In cylindrical coordinates, a point is also represented by 3 values. 1 angle, 2 lengths, and addition or subtraction does not work anymore in this case. Rotational motion of the links could be represented by a rotational matrix, denoted as capital C. The simplest ones are called elementary rotation matrices, which are rotations about the 3 axes in a Cartesian coordinate system. The elementary rotation matrices in their diagram are shown here. So to better understand these rotational matrices, let's have a look at an example. If we have a vector r, its representation in the frames after and before the rotation could be mapped with the rotational matrix, just like in the equation shown here. When we only look at the x and z coordinates and zoom in, you would see that geometrically this makes a lot of sense. Another way of understanding the rotational matrix is that it is essentially the projection of unit vectors of the frames. All rotation movements could be decomposed into combinations of elementary rotations. And to get a rotational matrix for the movement, you just need to multiply the elementary rotation matrices in order of occurrence. To get the vector after rotational motion, simply multiply the rotational matrix with the vector. This could also be used to transform the coordinate frame of the same vector. Normally, a robot consists of more than just one linkage. Therefore, it has more than one joint. To describe a robot's configuration, we could use the angles of all of its joints, or only the orientation of its end effector. So these 2 options correspond to joint space and task space. So here we show an example in 2D only, to help understand joint space and task space. Please note here that although they are represented in the form of a 3D space, they are essentially different from the Cartesian space that we introduced earlier. You can probably already tell by just looking at the notation of the axes. For a robot with full degree of freedom in a space and no redundancy, the number of coordinates in the joint space and task space should be the same. Let's look at these detailed calculations and equations in the robot kinematics. As a note here, our first demos were run open loop and they did not compute fingertip pose explicitly. So therefore, we did not write out the equations for the kinematics. However, as you can probably guess, it's certainly necessary to do so. So students would benefit from understanding kinematics to control the robot arm later on. With this diagram from the previous part, let's first understand what forward and inverse kinematics are. Forward kinematics give the end effector configuration as a function of the joint coordinates. That is the process of going from joint space all the way to task space. It maps the changes from the joint to the task space. The inverse kinematics, as the name, you guessed right, as the name suggests, gives the joint angles as a function of the end effector configuration. It is used when you know the desired end effector position and you want to find the joint angles needed to achieve this. This diagram on the right side gives you an idea of the relationship between forward and inverse kinematics between joint and task space. One thing often used in calculating kinematics is the homogeneous transformation matrix. It is denoted with the capital T. It contains both the translation and rotational changes from one joint to the other. Here in this example, the translational change would be the vector RAB represented in the frame A, and the rotational change would then be the rotational matrix CAB. For a robot with only rotational joints, the translational change is the link length and the rotational change would be the rotational matrix, which corresponds to the joint angle. Homogeneous transformation matrices are often denoted as T. Here in the example, T underscore AB is the homogeneous transformation matrix. So when there are multiple joints, just like the rotational matrices, homogeneous transformation matrices could also be multiplied together to get the matrix from initial point to the end effector. Here we use Q to represent the joint angle. Therefore, here we could get the forward kinematics as follows and the end effector position and rotation as is also shown here. If you do the calculation for the homogeneous transformation matrix TIE, you will find the first and the third value of the last column to be the same as the first two values of the end effector position here. This is decided by the fact that our example is in 2D. So y-coordinate values is by fact an example that is always here in this case 0 because of the 2D scenario. So when you look at the definition of the homogeneous transformation matrix, the last column always stands for the vector from origins of one reference frame to the other. So knowing the forward kinematics, can we also map the joint angular speed to the end effector speed? The answer is yes. In forward kinematics, the end effector is a function of joint angles. To get the speed, one just needs to differentiate the forward kinematics for one time. Then we would get an equation with the end effector speed as a function of the joint's angular speeds. This mapping is called forward differential kinematics. Its equation is as shown here. The matrix J here is called the Jacobian. It's basically mapping speed from joint space to task space. The Jacobian here is normally called the analytical Jacobian, and we denote it with the capital A. So we just went over the main steps that students will see when simulating with their robotic hands. Now we know what happens when we press that start button on our simulation. So we just went over the main steps that students will see when simulating with their robotic hands. Now we know what happens when we press that start button on our simulation. So far, we have been talking about robot dynamics based on conventional robots, which only consists of linkages and rotational or linear joints. The Franker arm falls into this category, as well as some other robotic arms from well-known companies such as ABB, Fanuc, KUKA, and so forth. For these robots, an encoder at the joint would be sufficient and precise to control the movement and position. As we have been introduced before, there are different types of joints we could use in a robotic hand. There's the pin joint, the flexure joint, the synovial joint, and the rolling contact joint. The kinematics of a pin joint is fairly simple, as it is equivalent to a rotational joint in 2D. The kinematics formula would be just a rotational matrix. Similarly, for a synovial joint, if we set the center of rotation at the center of the ball side, it would just be a rotational joint in 3D. The equation would be more complex, but the essential idea is still the same. So for robotic hands like the 5-hand, all joints are rolling contact joints, which means they do not have a fixed axis of motion. The rolling contact joints on the 5-hand are controlled by tendons, and we assume they are not being stretched. So therefore, as the length of the tendon channels inside the hand do not change, the length of the exposed tendon should not change as well. and could be used in the dynamics control of the 5-hand. Here we show simulation and a picture of a rolling contact joint and how tendons are attached on the joint. Green portions show the part of the tendon that changes the length, and the red portions show the parts of the tendon that is inside of the channels. So in the case of a 5-hand, we want to be able to map from joint angles to motor positions, with which we'll be able to know the tendon length and thus the fingertip positions. To achieve this, we need to get the tendon length change based on the joint angles. And since the tendon length inside the rigid parts of the 5-hand do not change, we just need to find the exposed tendon length. Here we consider two cases, a cylindrical rolling contact joint and a conical rolling contact joint. Here shows the schematic drawing of these two types of joints. The exposed tendon is the vector RT1, T2. Theta is the joint angle. The two Cartesian coordinate systems 1 and 2 are body fixed to the center of the two parts of this rolling joint, with x_1 and x_2 pointing in the direction of the rotation axis. For a cylindrical rolling joint, we can look at it in 2D, while in a conical rolling joint, it has to be in 3D. For cylindrical rolling joints, we use an auxiliary coordinate system, 0, which points to the current line of contact with its z-axis. With this, the exposed tendon length could be expressed as follows. R is the radius of the rolling cylinders, and R1, alpha1, and x1 are the cylinder coordinates of the points T1 in the coordinate system 1. R2, alpha2, and x2 are the cylinder coordinates of the point 2 in system 2. So that means C1 to 0 and C1 to 2 are the rotation matrices mapping the coordinates from system 0 to 1 and from system 2 to 1. They are shown as we are showing it here respectively. In the case of a conical rolling joint, the origins of all three systems 0, 1 and 2 lie at the tip of the cones. With the same variables as in cylindrical rolling joints, the exposed tendon length is expressed as shown. The C12 here is a 3D rotation. Its equation is shown here as well, with beta as the tip angle of the cones. So the two rolling joint cases could be generalized into one equation, with C10 expressed as a 3D rotation matrix. The beta angle is set to be 0 in the cylindrical rolling joints, and R is set to be 0 in conical rolling joints. When summing up RT1, T2 of all the joints on a tendon, we can get the length of the exposed tendon. To get the motor displacement for a specific joint, the angle combinations are important. We just need also to subtract the exposed tendon length with all joint angles equal to 0. This value could further be used in control algorithms of the 5-hand. So now we know how to map the position of the fingertips from the joint angles and further find the corresponding motor displacement. But for a hand to work, only position control is not enough. Proper force at fingertips are needed for holding an object. And for this, we need to be able to map the force needed at the fingertips to the motor torques. The Jacobians needed for this purpose. So we already know from previous discussions that the mapping between motor and joint positions can be expressed as P is equals to G of L, and that is equals to G of F of Q, and that is capital F of Q. So the P here presents the motor positions. It is a function of the tendon length L, which is further a function of the joint angles Q. That is, motor positions are also a function of the joint angles. In the case of the 5-hands, a single finger only consisted of two active joints, which is the MCP flexion and the PIP flexion. They are controlled by one motor. We hereby define the muscle Jacobian matrix Jm as follows. So in the discussion from before, where we talked about the Jacobian, From that, we know that the Jacobian maps the velocities of two parameters. In this case, it would be the velocity of the finger joints with the velocity of the motors. So from the energy perspective, the work done by the joint torques, tau, must be equal to that of the motor torques, t. It's essentially a capital tau. So that is to say they should have the same power. So therefore from the two equations we could get the equation here. After cancelling out the q dot and taking the transpose on both sides of the equation, we get the very last equation relating the joint torques and motor torques through the Jacobian. So similarly, we know that the velocity of the fingertips can also be mapped from the velocity of the finger joints using a different Jacobian. Thus, the joint torques also fulfill the following equations. So combining these two equations of joint torques, we can get the motor torques as a function of the fingertip forces. In this tutorial, you've learned how to model the kinematics of a conventional linkage and rotational joint robot. We use the knowledge of things such as the representation of point and linkage in a different coordinate system, rotational matrices, joint and task space, homogeneous transformation matrices, and the Jacobian. So you have learned how to perform the forward and inverse kinematics, and then you expanded and applied this knowledge further on non-conventional robots like the 5-hand. With this specific case study of the rolling contact joints on the 5-hand, we end up analyzing and developing the kinematic equations based on its physical structure. We also then modeled the dynamics equations of the 5-hand. This is also vital to know, as for a robotic hand, you want to manipulate an object, the forces are just equally as important as the position and orientation of the hand. Now we know how to get the kinematics and the dynamics equations for a robotic hand with rolling contact joints. In the next tutorial, we will further explore how we could use them in the control of a robot hand. We want to achieve tasks such as handling an object. To give you a heads up, we combine the kinematic equations we have with the Kalman filter, use reinforcement learning methods to train the hand on a specific task such as rolling a tennis ball. We then use reinforcement learning to train the 5-hand and also get into domain randomization as necessary.